So we had an equation that was like exactly like this, except our vector v. So just so you know, like vectors are typically written in like thick or with an arrow above it, since it's hard for me. I don't want to change the thickness of every time I write. I'm just going to use the arrow notation up top. So this v is a vector. In our case, this was like the C1 and the C3. And this value lambda, that's what we were calling R1 in the previous example. So we had an equation that was exactly R1, C1, C3 was equal to A, B, C, D times that. So it looks exactly like this form over here, again, where the V is C1, C3, and lambda, we usually use lambda to denote eigenvalues, is holding the place for R1. And so if we do some arithmetic with matrices, namely, I can subtract this vector, because it's a vector, from both sides, bring it over here. Then what's left over is just a zero vector over here. And then we can actually do some subtraction between these two matrices. And I can write this equation like this. And once we've got this vector in this form, we can see the only way I take a non-zero vector times some matrix and get the zero vector over here is going to be if this matrix has a determinant which is 0. So let's kind of just take a look at an example just to make sure we're comfortable with doing eigenvalues. Just to do some scratch work. And I'm going to just make up a matrix, so the eigenvalue might not work out particularly nice, but that's okay. Okay, so here's my matrix. And the question here is find the eigenvalues. Call this matrix A. So the way we do this, and this would be true whether I have a 2 by 2 matrix or a 20 by 20 matrix, is we subtract lambda, this eigenvalue, from each diagonal entry. And lambda is an unknown that we're going to solve for. And lambda is going to be really useful because it's going to tell us what powers we should use in our exponents in our solutions. So let me say step 2 would be to set up the characteristic equation. And the way we do that is we take the determinant of this matrix and we set it equal to 0, not the 0 vector, right? Because when we take the determinant of a matrix, we get a scalar number. And so when we take the determinant, at least for a 2 by 2 matrix, the calculation is a little bit easier. We just take the product of the two diagonal entries. And then we subtract the product of the off-diagonal entries. So it's kind of a three-step process. You know, first you've got your matrix, take the determinant of that matrix, and then solve the resulting equation for lambda. So this would give us like 18. What do we get here? Minus 9 lambda plus lambda squared plus 2. And we just witnessed a miracle here because this actually factors. I cannot believe that. That's probably the first time I've ever come up with a random matrix that has like integers as eigenvalues. Yeah, but now this factors into lambda minus 5 and lambda minus 4. So this matrix has these two eigenvalues, and let me just say that once we think about how we can set up this matrix from an initial problem, you can see that this is going to tell us exactly what these two powers would need to be in my solution. And that's going to be the power behind those. So rather than go through that long, drawn-out process that we kind of did to see where these equations come from, the nice thing is that those equations are, again, by definition, asking us to find the eigenvalues for that matrix.